Okay, so we're going to do lecture 4. I'll try to get through this as quickly and as painlessly as possible. I have my pen tool again. Okay, we're continuing this discussion with vectors, and now we are moving on to position vectors. A position vector is basically 3 coordinates in space as defined by this IJK coordinate system, and then the vector extends from the origin. So if you have some kind of coordinate system, you go out here, you say, okay, x is 5, that's here, y is, I don't know, 3, and then z is plus 2, and the point is somewhere right there. All you do is extend the vector from the origin, and then that gives you the magnitude and direction that it's moving in. So all that information is kind of baked in here. So they just have an example of a position vector here, and basically I just did the same thing as this example down here, right? So you have XYZ coordinate system, then you have the origin, you have this point you found out here, and you just extend it beyond that. Okay, so a change in a position vector is a displacement. So this is saying R2, R1. If we break it down into components, the original place was right here, X1, Y1, Z1. Now we've moved that vector over to whatever X2, Y2, Z2 is. This will make more sense as we go into it, but this is just an introduction. So they're just saying the overall change of the vector is accordance to its change in its components. Okay, so same deal as before. This is a position vector. These are position components in XYZ form. So when you take the derivative in respect to time, you get a velocity, is what it's saying here. So the individual components, you can each take a derivative in respect to time, or in this case, divide by time with the change, and you're going to get the components each, right, if you do them individually, because you can distribute this denominator. Okay, so that's just an example, and you have basically the x position and the z position just in the IJK coordinate system, and then divided by 2 seconds, so there you go. Okay, instantaneous velocity. Instantaneous velocity is a specific thing. So you're looking at the velocity at one moment in time of a position's movement. So I'm just going to jump down to this example down here. Basically, what we said in the previous slide, I'm going to jump back, well, 3 slides ago, where you have this x2 and x1. Now we're going to jump back to the visual version of this, where you have this first coordinate right here as defined by what would be x1, y1, z1, and then coming from the origin out to this, that'd be the first vector. And then now you have this second vector over here. So you can tell that the particle is moving from here to here. This is the actual movement it's making. If you want to find its instantaneous velocity, that means you're taking a single moment in time. So we're looking at a single time. So there is no change in time. It's a single time. When you look at that, you can see here that it is equivalent to the tangent of that position. So if you see, we have a vector going up here and one coming out here. If you break this into components, it should be something along the lines of this. If I can draw it straight. So the tangent is then out perpendicular to that vector. So that tangent gives you the instantaneous velocity, is what they're saying. And then here's just another visualization of the tangent. The tangent's moving through here. So they're saying that the x and the y velocity, this direction. Yeah, so hopefully that makes sense. So that goes back to the direction of the instantaneous velocity of a particle is always tangent to the particle's path at a particle's position. So if we were to go back to this and we look at this position right here, the instantaneous velocity is going to be different. It's going to be more along this way. So you can take the instantaneous velocities at each point, and they should have different tangent lines. So again, you're taking the IJK coordinate system, and then you're distributing this derivative in respect to time on a position, and that's going to give you the velocity. They're saying if you want to take the individual components, if you just want the x component of the velocity, then you just do dx dt, etc. dy dt for the y component. Okay, so here's the checkpoint. Figure shows a circular path taken by a particle. Instantaneous velocity is this. Through which coordinate is the particle moving at that instant if it is traveling clockwise? So if you go clockwise and you go to 2, and that's a positive 2, and basically the x direction, in this case it's the I direction as noted here. So it's a positive 2, and then a negative 2 in the j, so that means it's moving downward. So basically it's coming this direction, as indicated by the answer here. And then if it's moving counterclockwise, then basically you're just in the third quadrant instead of the first quadrant. It's coming around this way. But basically we're looking at that instantaneous moment in time. We'll say it's right there. So this thing's going round and round, and we just paused it. Pause. We're going to look at 2, negative 2, and then we're going to say, okay, it's moving still in a circular direction, but the tangent is right here. That's how we're determining that instantaneous velocity. And we'll get into this later too, but things moving in a circular direction, they are always accelerating, because if we were to look at this point here, then the instantaneous velocity is going to be something like that. Here, it's going to be, something like that. And as it moves around, you can see that no matter where you are, the vector is constantly changing. So if I took it just, a millisecond past this point, the vector is going to be slightly different. The vector direction is constantly changing. The magnitude stays the same. So this still counts as acceleration, even though it doesn't seem like it, because everyday real world stuff, we think of acceleration as going faster, right? We think about the magnitude increasing. But in this case, the direction is just changing, and that's why it's accelerating. Okay, now we're doing average acceleration, and we're looking at that as the change in velocity, and we're dividing by that by the change in time. And so then if we go to the instantaneous acceleration, then we're taking the derivative. So that's a single unit time. And this works exactly the same as what we just did with the position and the instantaneous velocity, right? So the only difference is we've changed, before it was dx dt, and that gave us the instantaneous velocity, right? So now, not so you get this confused, because there's like a little dot there. So now we're just doing the acceleration. You basically plug in the velocity this time, take the derivative in respect to time, and you're going to get this acceleration. Same deal, you can break it up into components. If you do this, this derivative is distributed to all 3 coordinates, I, J, K, and then it's just showing it distributed here individually. So we're saying here, same deal as before, the velocities, you can divvy them up into just the x component, y component, z component. You just take the derivative of only the x components of this. So anything that would be here, acceleration that's in the I component, you'll take the derivative in respect to time. That's going to give you all the x components of that vector. And again, here's just another visual representation. It's more the same of what we just did. So again, they're saying that, as with the velocity, the acceleration vector does not extend from one point to another, only shows the direction and the magnitude. So basically, don't look at 2 points and then take that as the acceleration. It's not necessarily true. So here's another checkpoint. Here are 4 descriptions of the positions in meters of a puck as it moves in the XY plane. So basically, this has been reduced down to a math equation. We're just doing math on this. And it's asking, are the x, which is right here, and y, here, acceleration components constant? is acceleration A constant, the vector A. So basically what it's saying here, and I'm going to try to squeak this in little places, you have some x, and we want to get an acceleration component out of it. So in order to get the velocity, you have to take the first derivative in respect to time. Now, we have the x, that's the first position. We take the first derivative in respect to time, and then if we want the acceleration of it then, we want to take the second derivative. So I'm going to write it like this because it's not written like this anywhere in the PowerPoint. So when you have the position, which is this x, you take the derivative twice, and that'll give you acceleration. If you take the derivative once, that gives you the velocity. So if we do example 1 here, we have minus 3t squared plus 4t minus 2. So if this is x, I'll put x equals here. If that's x, then we have to do dx dt, right? So you take the derivatives of this once, you're going to get negative 6t. Derivative of this is then plus 4, and then this goes to 0. So then we have to take the second derivative of it, and write this over here. So now we're taking the derivative again of this. We take the derivative of this. You're going to get negative 6. This then goes to 0. This we now look at, and this is a constant, right? There's no variable. If there was a variable in there of time, then that means with time that this is changing. But it's a constant, therefore it is constant. So this first x part, as indicated here by the answer, is yes, this is constant. If we, now that's the only one I'm going to write out. I'll just kind of voice these because you should be able to do them in your head, if at least once you get good enough with derivatives and stuff. We do the y component. So you take the first derivative of this portion, you're going to get 12t. Then you take the second derivative of this portion, you're going to get 12. So that part's constant. Take this once, you get 4. Take it twice, you get 0. That means that, yes, this is going to equal just 12. So this is going to be constant. There's no other variable in there that's changing anything. So the x portion is yes, the y portion is yes. Then basically we're saying that the vector A, which is both components combined, so first one's yes, the second one's yes, therefore the total of them is yes. If we jump to number 2, now you have a number 3 exponent up here. So when you do this, you take the first derivative, you get negative 9t, but then you still have a squared up here, so then it becomes 18t, or 9t squared, and then goes to 18t. So you still have a variable in there. So that means as time increases that this number is changing. Therefore, the acceleration is not constant. It's changing constantly. So here you get no. We don't have to do the second part. The first part already answered the information. So if we do the second part, you're going to get 10t. We do the derivative again. You just get 10. And then this goes to 0. So again, it's just 10. It's going to be constant. So that means yes. When you do both the components of these as you add them up, one's already changing. Therefore, the total has to be changing. So is the total acceleration vector constant? No. We jump to number 4. Same deal. We already know we have an exponent to the third power, so that this is not going to result in 2 derivatives, leaving us with a constant. You're going to still be left over with a t in there, which means you have a variable, which means this is changing. So I'm doing kind of like shortcuts. Once you get intuitive into this, you don't have to do all this work. I can look at this immediately and say, no, this is not constant, this is changing. So the x is then no. And again, it's split it up into the components. I guess I went to 4 right away. So I'm doing 4 just in case you didn't notice. But they've split it up into I and J to get used to the IJK system. So this is the x portion, right? This is the y portion. So like I said, this is not constant, so this is no. When we do just the j portion, which is just the y, this is just a single constant already. It's going to be reduced to 0, so it remains constant. So this is yes. So again, one's constant, one's not. Therefore, the total is not constant. So the answer is no. If we go back to number 3 real quick, because I skipped it, this is a second derivative. We're going to take the derivative twice. Therefore, we know this is going to be constant, which is this portion. Same thing. This is a single variable t, 2 derivatives is going to result in this being just 0. This is also going to go to 0, so we know that this is constant. Yes. Therefore, both of them are constant. Therefore, the total acceleration is constant. Yes. Okay, a projectile. We're going to move into projectile motion. A projectile motion will frequently go one of two ways in these problems. You're going to have some sort of land, and then you're going to have something that is launched from an initial position and then goes over and lands. So this could be a football. Football player throws a football. A baseball player throws a baseball. A cannonball is shot from a cannon at such a velocity as it moves through this trajectory and lands right here. It doesn't matter the means in which it's moving. Basically, there's an initial push right here, and then that's it. There's no more energy put into the system. It moves along of its own accord until something stops it, which is the ground over here. So when we define this, it's a particle moving in the vertical plane, right? So a particle has to be moving up and down. It has some initial velocity, like I said, that should be baked into the story, whatever, football player, baseball player, cannon, etc. The acceleration then is always prone to the free fall acceleration of g. So constantly, no matter where we look at this, g is pulling down on it, right? Got it here, g is pulling down. Here, g is pulling down. So what's happening, and just to clarify, this is going to be like a single projectile moving through this. If you have like some kind of rocket ship that's shooting out, this is not considered a projectile, right? Because there is constant force on the back of this propelling this thing forward. So this is not what we're talking about. We'll get into rockets and stuff later. Again, the projectile is defined as something that was launched initially, and then nothing else acts on it except gravity. So again, the acceleration on this is always pulling downward. So it's launched initially with some upward motion. So there is a y component of this, right, and an x component. If we look at just the y components, gravity is constantly fighting against it. So as it goes up, eventually it loses that initial momentum it has moving upwards until the vertical velocity becomes 0 at the pinnacle or the apex of the trajectory. Once that happens, then gravity takes over and starts accelerating it downwards. So the velocity starts increasing in a negative fashion. So here we can see velocity is plus and it is decreasing. And then we can, over here, we can see velocity is negative and it's increasing. Right? As it goes farther and further down, it's basically increasing in velocity. It's going faster and faster until it hits the ground. Okay, then again, you can break up the x and y components of the initial velocity that you're given. Again, use your cosines and sines to break these things up. Again, they're saying that these two are broken up, and we'll get more into this. So what we're saying is we learned one-dimensional motion originally. When we have two-dimensional motion, all we're doing is basically combining two one-dimension problems. So you have the x component and the y component. If you break those two up, then you're just dealing with the one-dimensional problem in both the x and the y. Another checkpoint here. As a certain instance, a fly ball has a velocity of this and this. The x-axis is horizontal, the y-axis is upward, v is in meters per second, has the ball past its highest point. And what we're saying here is that basically when something, they all kind of follow the same trajectory. And we're looking at the eye is going to be constant. As this thing moves through the x direction, the velocity does not change. It is constant. If we look at the y direction, like I previously stated here, it's decreasing. So velocity is not constant in the y, but it is constant in the x. So as it's going up, it has, if I draw this as like a magnitude, it has a longer magnitude, and then the magnitude gets shorter and shorter until you get up here and there's no magnitude anymore. Because it's moving, the vertical part has no velocity, it's hit 0. As it comes down, then it's in the negative direction. The magnitude gets longer and longer because the speed is increasing. Here the speed is decreasing. So when we look at this, we can see that it is whatever value it is, it doesn't matter, but it's negative. That's because it's moving downward. So as I said, the answer says yes, the y velocity is negative, so the ball is now falling. So we know it's in this half of the trajectory. So go in a horizontal motion, like we said, there's no acceleration. The velocity is constant. So you can use these equations. The vertical motion, again, is not constant. So it has an acceleration, which is this portion. So this portion originally had the, if I put the same thing, gt squared, this doesn't actually exist because this isn't in here. So this is just acceleration. Then we say, what's the acceleration? It's 0. So it goes to 0. Therefore, the whole piece goes to 0. And then this is gone. So we're left with just the initial velocity times the time. So the vertical motion, you're using the full equation, right? Because you have the acceleration in here. Okay, so what's happening here? And I don't like this order of slides it's going in. All they've done is taken those previous two equations. They said time in both directions is the same, and they've combined those two equations. So that shouldn't be very tricky. They basically just said that time and time here are the same, and then they solve for time, and then set them equal to each other, and then solve for y, right? So the times eliminate themselves. If you want to know why this is, because this doesn't make a whole lot of sense, there's a famous experiment in physics. It's called like the bullet drop problem, and they did it on Mythbusters. You can definitely look it up on YouTube. They did it on Mythbusters. But basically, there's a guy with a gun here. There you go. There's my gun drawing skill. And a bullet is fired from the gun. Right? So the bullet comes out and it follows some path like this. And we'll say this is the ground. It's not supposed to be uphill. I just can't draw a straight line with this goofy mouse pen. There is a second bullet, we'll say back here, in which a person is holding. So you have bullet 1 and bullet 2. Bullet 1 is simply dropped. It's not in the gun. It's just sitting there. It's in the guy's hand. He drops it. So it goes down. And it lands here. This bullet is fired from the gun at the exact same height. These are the same height. So the bullet starts here, and then it falls here. The interesting thing is, and it's kind of hard to imagine, that it doesn't matter how far this bullet flies. This could be a quarter mile, half a mile, 10 miles. It doesn't matter. The time that the bullets are in the air are the same. Because even though this has an X component propelling it forward, the Y component is the acceleration of gravity, and it affects them both equally. So the time it takes to fall from here to here is going to be the exact same time that this bullet flying out of the gun takes to go to the ground. Now, Again, I'd look up the video. If this doesn't make sense, it might make more sense if you watch like Mythbusters or something. But this is a fundamental piece of information for these projectile problems. This is the key linking factor for these guys. So if you have something, we'll say in a projectile motion like this, basically, if you split this in half, it's just a mirror version of itself, right? It's going up, hits some point 0. Now here it starts at 0, goes down, and hits the ground and stops. So if we look at this point right here, this is the max height of it. If we just dropped something from right here down, then the initial velocity, we have that information already. Almost all these, well, I won't say almost all. A lot of these problems you do, they won't give you the initial velocity. They'll just say like a projectile is fired from a cannon at some initial velocity. It doesn't give you the information. So if we go to the pinnacle of it, and we have extra information that they give us, you can say the initial velocity here is 0, and then you can find the time it takes just to fall from here to here. So this will give you the time. When you have this time is in one direction. So that's the exact same time. That's the same situation as I drew over here. This time that it took to go from here, essentially, to the same height, if we were right at the beginning, is the same as the time it took to fall. So this is going down, this is going up. So the amount of time it takes to go up and stop is the same amount of time it takes to start at 0 and then go down. So essentially what you've done, if you've solved for time, now you have time here. You have time here and here. And if we just multiply this by 2, the pen works, you have the total time. So you know the time it took to go up, you know the time it took to go down. If you just multiply the single one you solved for, you multiply by 2, that's the total time. So this is the key piece of information solving these, because you're going to eventually do these and it's going to be like, okay, I have an X, I have a Y, whatever, other pieces of information. We'll say V, acceleration, I don't know, and time. When you do these, it's going to be like, 5, 6, 7. I probably didn't do that. We'll say this is a mystery. I'll make that a question mark. And then acceleration is just gravity. And then you're missing time too. So you're like, oh no, I'm missing 2 variables. I can't solve for this. This is where you get it from. You have to piece that from here. Then you solve for the t, you plug it in here. Now you're only missing 1 variable. And you can use your regular kinematic equations that we learned to solve for that 1 variable that you're missing. So again, I'm going to go through these a couple more. Hopefully it'll make more sense as we go. And this is just another horizontal range problem. This is, again, just a kinematic equation, basically reduced. I would just use the kinematic equations. You can use these as shortcuts if you want. Just don't forget the original kinematic equations where this stuff comes from. And then, of course, it says the horizontal range R is a maximum for launch at 45 degrees. So just a little piece of information. Anytime you want to find the optimal distance something travels, a 45-degree angle is the optimum. If you shoot it too high, it's going to take less of a path. If you shoot too low, same deal. It's going to take a smaller path. So 45 is the optimal, and that'll make it go farther. Okay, so here's a bunch of stuff that basically I just drew. You have the horizontal motion. So you have something that was initially launched like so. So if we break this up into components, they have just the Y portion here, right? The Y portion goes up to whatever, about that height if we match it with this one right here. So same deal. It's going to be, somewhere out here. That's the same height. This is just a graphical representation of the vertical velocity as it moves through. So it's going to go up, deaccelerate, hit 0, stop, come down, start accelerating, and then go faster and faster until it hits the ground. The X doesn't have that motion, right? The X is just continuous, just moving through here at a constant rate until it stops and it hits the ground wherever it is. So that's kind of the visual representation of what's happening here. Also, when you're breaking these up into components, that's what you're doing. It's one dimension and one dimension, right? So basically, I already explained all this. This is just sort of visually elaborating what I just said. At the very pinnacle, you can see that, or the apex, that it's the height is at a max and the velocity is 0. Okay, so this is again just a bigger version of what we were looking at before. You have constant velocity in the X, and then the Y velocity is changing. So we won't go into that anymore. And then again, if I use this as a better representation of that gun problem, draw a little gun again. Oops. Gun's getting worse. If we draw the bullet again, going through here, you shoot it, basically it's going to go this distance and keep the same speed the whole time it's moving. This is, of course, I failed to mention, this neglects air resistance, right? If we assume there's no air resistance, if there is no force that is stopping or slowing down the velocity of this, then it won't slow down. So Newton's laws, which we didn't exactly go over those yet, objects in motion tend to stay in motion unless acted upon by an outside force. That's what's being demonstrated here. The bullet moves forward, nothing acts on it because we've just magically eliminated air resistance. Therefore, it's just going to keep going. The only thing that's going to stop it is because gravity's pulling it down. But the actual velocity in which it moves is the same speed the whole time, right? So, and then, like I said, so the time it takes to go from here to here at a constant velocity is just time. And the time it takes to go through this whole thing is then the same as dropping it from here to here, right? So this equals time. That is the same time as this. This is the same. Okay, so I think you got the idea with this, hopefully. So again, we assume the air resistance is negligible, meaning that it is 0. We're not taking it into account. Basically, air resistance is complicated. So the same as friction is complicated. So you're not going to do any of that stuff probably as an undergrad period. You're going to get all the way to your senior year, whatever advanced classes you have, and then we're still going to say, okay, ignoring friction, ignoring air resistance, etc., because it's very complicated. You can do that stuff in graduate school. If you're an engineer, chances are you're not going to go to graduate school. But basically, we have computers that calculate this stuff because it is very complicated and it's very tedious. But it is not actually negligible if you look at the distance something's traveling. So this is like our no air resistance model that we're basing this off of. This would be a situation in which you add air resistance, right? It decreases the distance it travels considerably. It also decreases the height it travels at considerably, right? Because all of this is working against it and slowing it down. So although we are ignoring air resistance for all these problems, just don't take it to mean that it is extremely small and we can just ignore it. It is not. It's quite negligible, especially depending on the size and shape of the object that's traveling through the air, which should make sense to you logically living in the real world. Okay, checkpoint 4. A fly ball is hit to the outfield. During its flight, again ignoring air resistance, what happens to the horizontal, vertical components of the velocity? So again, same exact situation. It doesn't matter how colorful they make it with the story. A ball is hit into the outfield. During its flight, what happens to the horizontal? we've already gone over this. The x, nothing is affecting it. There's no force acting on it. The gravity is the only force being applied here, and that only applies to the y direction. So in the x direction, what happens? Nothing. It remains unchanged. Now it's saying what happens to the vertical components of velocity. Now this says it decreases, becomes negative. I'm not sure how they're wording this exactly, but on the initial ascent going upwards, the velocity is decreasing but positive. As it descends on the second half of the trajectory, the velocity is increasing but negative, right? Which is, I think, what this is trying to say. What are the c horizontal components of its acceleration? We already talked about this. It's 0. Gravity does not affect the x direction. And then they're asking about the y direction then for the acceleration, and then we've already established that gravity is affecting it at all times. Okay, this is kind of a brief blurb where we're tying in circular motion into these problems. And this is a point in which I was saying before. If something is traveling in a circular motion right like this, it has a certain speed it's traveling at, right? Meaning the magnitude of this thing traveling could be the same the whole way around. And in these cases we're looking at, they are in fact the same all the way around, meaning the magnitude is the same at every point along the circle. The thing is that, again, it has acceleration, but because the acceleration is constantly changing. So if we're using centripetal acceleration, centripetal means that it is pulling inward. Centrifugal is a fictional force, and it's pulling outward. It's something we use to counterbalance these things. Because if you have no force acting on both sides, that means this thing is either migrating towards the inside of the circle or pulling further and further away from the center. So these forces have to be equal at all points in order for this thing to maintain its circular path. But again, this is something for later. We won't worry about this right now. The only point is we're saying here is that we're taking the tangent of the position right here at every point. So if I took a point here, etc., it's like this. You can see that the velocity is constantly changing direction, which means there's an acceleration. And that's pretty much the whole point of what this slide is trying to say. Again, it's called centripetal acceleration. What we're talking about, that's the force pulling inward. This is the equation we use. One of the other good points is the period of revolution. When we say period, if we mark a point and we say this is the starting point, the period is the time it takes to go around one time. Right? So if it goes around 3 times, you'd have to multiply the period by 3. And you'll do a lot of this stuff in lab. So, and I mean, if you're not currently going to lab, then you'll see it in the lab manual when you do the labs that you were supposed to do. But again, just another equation. And that is it. So just a brief introduction to the circular stuff. It's mostly about the 2-dimensional projectile stuff. Hopefully this all makes sense. Again, like usual, if you have questions, let me know, and then I'll post the Chapter 4 homework later today.